Okay, so today we're going to look at doing function transformations. Again, function transformations are, you should be familiar with. In grade 11, you did some function transformations of some of the more basic parent functions. And in grade 10, you did some function transformations of y equals mx plus b, and obviously of a quadratic as well when you got into quadratics of the form, the vertex form. So y equals a bracket x minus h bracket squared plus k. We're going to continue on with that, and it should look familiar because there's a lot of overlap. So function transformations generally all take the form of y equals, let me go back up here and get my pen, y equals a f at bx plus c plus d. Now, the letters here, A, B, C, and D, they can change depending on who's at the helm and what textbook you're looking at. And in fact, the kind of the general form might look subtly different. We're going to talk about both variations. It could also look like y equals A bracket F or F bracket B. And then sometimes people will also factor out the B from within the brackets. And there's definitely an advantage to doing it each way, depending on the circumstances. And I'm amenable to you choosing either way. I don't care. But what we're going to look at this is we're going to look at each one of these variables and kind of indicate what effect that they have on the final function. So it's probably easiest to look at it, believe it or not, in terms of a function like a periodic function, so a sinusoidal. So as an example, if we were to look at y equals the sine of x, you might think, why on earth would we ever want to do a sinusoidal? But believe it or not, it actually lends understanding. So if we just do a really quick function of y equals sine x, so if we look at this function of y equals sine x, the parent function we know looks something like this. It starts at 0 and goes like this. It has an amplitude of 1, so it's going to go between 1 and -1. And for now, we're going to think that this is 180 and this is 360. So in a little while, we're going to learn how to do that in radians. But for now, we're going to do it in degrees. So there is the parent function y equals sine x. Some of the things are going to be really obvious. So the a actually affects two things. It can change the vertical stretch or compression. So a vertical stretch or compression, And the other thing that it can do in theory, depending on whether it's positive or negative, if a is positive, it doesn't really do much. But if a is negative, in the case that a is less than 0, it can also be a reflection across the x-axis. So if we look at it, really, really basic one. So if we did, for instance, y equals 5 sine x, and then we did a really quick sketch of that. So because it's a vertical stretch, it doesn't do anything to the horizontal component of this function. But what's going to happen is it's going to be substantially stretched like this. Forgive the fact that my graph isn't terribly symmetric, something like that. But now the amplitude is 5. So that's 0 there. And then this is going to go down to -5. But the period length hasn't changed at all. So this is still 180 and this is still 360. So what the A has done here is it has stretched. It has basically taken every component that used to be a certain distance. So if the distance away from the x-axis used to be 1, it's now going to be 5 away because it affected a vertical stretch of 5 times on the vertical axis. Okay, so that's what the A is going to do. If A were negative, what it would do was turn the whole thing upside down. It would go the other direction. So A affects the vertical part of the function. If we think about let's do the D component next. That's the next easiest one. So what D does is D is simply a vertical shift. All it does is it takes the whole function and it moves it up or down exactly D spaces. So if we did a really quick y equals the sine of x, instead of being 5 sine of x, we do sine of x plus 5, what it's going to end up looking like is I'm going to just draw it like this, and I'm going to kind of think, all right, so now it's going to be shifted up 5. So sine x used to be symmetrical about the x-axis. Sine x is now actually going to be symmetrical about y equals 5. So it's got an amplitude of 1, which will let it go up to 6 and down to 4. And so then sine x should still look pretty much the same. And if we come down here, this is still 180, and this is still 360. So the d value is the absolute easiest. D is simply a shift up a certain number of spaces, d spaces, or down d spaces according to the sign of d itself. If d is positive, it's up that many spaces, and if d is negative, it is down that many spaces. Okay, so let's grab us another page here. So file, do a new page. I don't want to, I'll save my old one. Actually, never mind, I won't save my old one. Okay, here we go. So we still have y equals a f at bx plus c plus d. So we've kind of looked after a, we've looked after d. Let's consider what b does. Okay, so b, instead of working on the vertical, b actually impacts the horizontal. So b does it's kind of the accordion stretching variable. It either compresses it inwards or it stretches it outwards. So b is a horizontal stretch or compression. Stretch or compression. And the interesting thing about stuff that is inside the brackets, it's really interesting. Everything that's inside the brackets, so both the B and the C, the stuff inside the brackets kind of works opposite to what you expect. So that means for B values greater than 1, you actually get a compression. For B values between 0 and 1, what we get is we get a stretch by that factor. Okay, so it's stretched if it's between 0 and 1, and it is compressed if it's greater than 1. And if B value is less than 0, meaning that it's negative, we actually get a reflection across, this time instead of being across the x-axis, it's actually a reflection across the y-axis. So let's look at how that pans out. So let's really quickly get y equals sine x up here again. So just get the parent function. So we've got it for reference. Okay, so here's going to be my sine x really quickly. So sine x, we know, goes like this. It has an amplitude of 1 and an amplitude of -1 down here. There's 180, there's 360. Now, if we were to actually add an equivalent b value to the mix, so if we did y equals the sine of, let's make it an easy number. How about if we did the sine of 3x? So we can see our b value here is 3. Well, that means that b is actually greater than 1. So we're going to end up getting a compression. So it used to be that our period length is 360 degrees. What this actually does, the 3 inside actually takes basically the distance that every point that used to exist away from the y-axis, it takes that distance and divides it by 3. So where this point used to be 180 degrees from the y-axis, it's actually now going to end up being at 60 degrees. And where this was 360 degrees, we're going to take and divide by 3, and it's going to end up being 120 degrees. So this is actually going to end up with a period length of 120 degrees, where the standard sine function is actually a period length of course, 360. So I'm going to really quickly go ahead and sketch this. So it doesn't affect the amplitude at all. So it's still going to have an amplitude of 1, so it can reach up to 1 and down to -1. And it's just going to end up being a much shorter amplitude. So this is now 60 degrees, and this over here is 120 degrees. Okay, so this has actually taken and compressed it. Whereas if we looked at y equals the sine of 1/3 x, if we look at that, this now, the b value is between 0 and 1, so we're going to get a stretch. So it still works the same way. In the same way that we divided each one of these points by 3 for this function, we can divide each one of these points by 1/3. So what's going to happen now is our period length is going to end up being not 120 degrees. We're going to take 360 degrees. And if we divide that by 1/3, we're going to end up with 1,080 degrees. Okay, so the sine function still is going to go from 1 down to -1. And now it's going to be a much longer period length. So amplitude's still going to be the same. So halfway now, if we did 180 and we divided it by 1/3, we're going to find out that it is 540 degrees. And the final period length here is going to be out to 1080. Okay, so what we've got there is we have that the B value is our accordion variable. It's going to either affect a stretch or a compression according to whether it's greater than 1 or if it's less than 1. And if it's 1, of course, it's not going to change anything whatsoever. So I would like to grab another page here. So File, New, and I'm not going to bother saving that one. And so now we just have the C variable left to talk about. So y equals AF at bx plus c plus d. And I indicated that there was another way we could write it. It could be y equals a f at b bracket x. Actually, normally in here it's going to be minus d. So let me just erase that. Not a great eraser. That's fine. Grab my pen again. And so minus c plus d. And it can be advantageous. I'm going to explore both of these. Actually, maybe I should do them side by side so that we can see what it looks like. So if we consider, we'll just go right back to using sine x again, simply because we can. So if we had y equals the sine of, let's say, x minus 30. Notice that the c has to be within the brackets. If we didn't have the brackets here, if we just wrote it as y equals the sine of x minus 30 without the use of brackets, that wouldn't then be a c value. That would end up being a d value. So that would simply shift it down 30. But this is inside the brackets, so this becomes our c value. So the period length hasn't been affected. It still has an amplitude of, or a b value of 1. So let me just get up the regular y equals sine x so we can compare again. So this is just going to be y equals sine x again. And so it still goes like this, and it goes from 1 to -1, and this is still 180, and this is still 360. Well, this one has a b value of 1, so it's still going to have a period length of 1, but the distinction is this minus 30 is going to do something. Well, this minus 30 is actually a horizontal translation. So the d value, or the c value, excuse me, the c value in both cases is going to be a horizontal shift. And I'm going to talk about how I do it versus how it might be done over here. I typically leave it like this. A lot of the textbooks and other teachers are going to show you this way, and I'm good either way. I'm always going to take what the entire argument within the brackets is. So here's my argument within the brackets. It's x minus 30. I'm going to take x minus 30, and I'm going to set it equal to 0. And then I'm going to solve for x, which just means I'm going to move the 30 over. So we're going to get x equals 30. When I take that expression that's inside the brackets and I equate it to 0 and I solve for x, the value that I get right here is the exact horizontal shift. So the number I get here tells me exactly what the horizontal shift is going to be. Okay, so the horizontal shift in this case is 30, and because it's actually positive 30, it means it is to the right 30 degrees. So this function is going to look like this. So if I kind of think, all right, here is 30 degrees, and it's going to have a period length of 360, so it's going to finish over here at 390 degrees. It's still going to have an amplitude of 1 and an amplitude -1 down here. So the basic sine function is still going to look like this, and of course it will continue and it will end up down in that vicinity, but it's taken and it's shifted that entire thing to the right 30 degrees. So if we don't have a b value, it's pretty obvious that we can just take and we can say, oh, it's going to kind of be the opposite sign. But the real reason is because we're going to solve for x. If it was written over here, in fact, this example wouldn't differ at all. It's going to end up being the exact same. Where it would differ is, imagine, that we wanted to do y equals the sine of, how about 3x minus 30, for instance. Okay, we know that this 3 is going to change the period length. The period length is going to be 360 divided by 3. So it's only going to have a period length of 120 degrees. And our instinct is going to say, oh, this is going to take and it's going to shift us 30 to the right. But in fact, it's not. It's actually going to shift us 10 to the right. And I can show you why. If we take the argument that's within the brackets and we set it equal to 0 and we solve, we're going to get that 3x equals 30. We're going to divide both sides by 3, divide by 3, and we're going to get that x equals 10. And as I suggested before, the value that you get after you've taken the brackets set equal to 0 and solved is exactly the shift that's going to happen. So because this is positive, it's actually going to shift and it's going to be to the right 10 degrees. And so this is written in this form over here. If I rewrite it in this form, it means that I'm going to have to factor this 3 out of these brackets. So it would look like y equals sine of 3 bracket x minus 10. So now you can kind of see, oh, there's where that 10 comes from. I still have a minus in here. The advantage is to this form that if I have a graph and I have to return it to the function, it's more easily put in here, and we'll explore that more deeply in class. So there's two different ways. So if we kind of do a synopsis, A is a vertical stretch or compression or a flip across the x-axis. B is a horizontal stretch or compression. Horizontal stretch if x is less than 1 but greater than 0. Compression if x is greater than 1. And it's a flip across the y-axis in the event that b is negative. C is a horizontal shift to the left or to the right. And the way I like to figure out how much it is I like to take the entire set of brackets, set it equal to 0, and solve, and the result is the exact answer. So in this case, we found that it's 10 degrees. And then D is the easiest one of the bunch. It's simply a shift up D if it's plus, down D if it is minus. And so that is what the function transformations are, and we've done it with trig. And in class, we're going to examine what it looks like to do with other parent functions.